Welcome everybody to our lecture in image processing, retrieval and analysis. Here is our menu for today. If you remember last time, we have been talking about the idea of mean filtering, which we may understand as yet another convolution. And then we saw that by intelligent reprocessing we can push the computational complexity of mean filtering to rather efficient regions or efficient computational behavior. So we will briefly recap that because once we were done with the mean filtering, we introduced the idea of median filters, and I promised you that we'll look into faster ways of computing median filters. This is what we will be doing today, and then I have a couple of things for you that are good to know, but we will not study them in detail. And I'll explain why when we come there, when we get there. So basically our topic for today is efficient implementations of median filters and then other funny stuff. Let's see. So once again, what did we do when we were talking about the mean filter? And this note is a different way of explaining that. Last time we started with the point of view of convolution. Now we look again at neighborhoods. So that is, we are given an image, let's call it F, and we're interested in local characteristics of F, that is, I don't know, brightness or intensity distributions within a neighborhood of size, say, m by n, and a neighborhood for every pixel. So in this sketch here, I have singled out a certain pixel, let's call it x and y, some pixel xy is this one, and then we have an m by n neighborhood, which in this example is actually sort of an n by n neighborhood, so m and n are the same value here. And given this pixel, we can, of course, look at the values of the pixels contained within this n by n neighborhood. And I shall call these neighborhoods calligraphic n xy, where this xy indicates the pixel we are currently talking about, and these sets, neighborhood sets, contain all the pixel values within the neighborhood we're interested in. And we may collect the pixels in this neighborhood and then call them, or the values of these pixels, p naught. This is important, all the way up to pq minus 1, where q is m by n. And it's actually really important that this is a 0 and this is q minus 1. And the idea of mean filtering is simply to compute a new pixel value for the pixel we are talking about. So we want to compute a new value for the guy indicated by the black dot, simply by averaging over all the pixel values contained in this set n, and here I'm writing np instead of nxy, but it's the same thing, you get that, right? Well, instead of pi, summing over the pi contained in here, I'll just give them a name, call them I. So this is just different ways of writing these down. This is the idea of mean filtering. We are given a neighborhood, say there is a certain center pixel. For this center pixel we want to compute a new value, and that is just the average or mean in this neighborhood. And we didn't do that last time, but just as well, we may consider different ways of computing averages. Right? We can think of having weights that would weight the contribution of every pixel in this neighborhood, and then we would sum. We have this weighted sum, and in order to make sure that this behaves as a statistical measure, we have to normalize this by the sum of over all the weights. Why would I mention that? It's just, pardon? Yeah, because of this. So you see, If we write it like this, we didn't do that last time, but if we write it like this, and if we generalize it like so, we recognize that the Gaussian filters we have been studying before are nothing but weighted mean filters. Because in these, when we do convolution with the Gaussian, we actually do have these weights here. Those are the values contained in the convolution mask. Right? And we spent some time on discussing how to compute that, or how to compute the values for a one-dimensional Gaussian convolution mask at least. And yeah, the way we computed those, this normalization was contained in our computation. Right? But you do not necessarily have to do it the way we did. If you don't, then make sure that you normalize your filter mask correspondingly. If you want to compute some sort of a mean, right? If you want to compute something wild, you don't have to worry about normalization. But if you're interested in the idea of a mean or a weighted mean, then please make sure you normalize. We went on studying the complexity of this idea, and well, we consider these mean filters in terms of convolution masks and convolve the image with these masks. We know that the effort per pixel is of the order m by n, because we have one outer for loop, two for loops, one over the rows, one over the columns of the image. So we have two outer loops to process every pixel in the image. And then for every pixel in the image, we would have, again, two for loops over the rows of the mask and columns of the mask. And so therefore, if we were to compute mean filters using convolutions, we would end up with complexity in the order of m by n per pixel. We saw that this can be pushed down to a constant that is O of 1 computational complexity. And here is how that went. This time I decluttered, decluttered the equations. So what we're basically interested in computing is a loop image C, where for every coordinate in C, depending on our current choice of the neighborhood size we are interested in, we would have to compute this. Right? This is again just the summation we just saw. This time it makes it explicit that we have columns and rows in the image. But this is again just the computation of the average value within that neighborhood. This is our problem, and yeah, that is of complexity m by n if we do it naively. We then saw the idea of computing these so-called integrals of integrals, because in a sense this is already an integral, integrates over something. And this image capital C of x and y has the following property, that at a pixel x and y, it contains the sum over all, and this again without m&m indicates just the value of the original image, over all the values to the left and on top of it. Right? We assume that the with all of this, I'm assuming this is now a matrix representation, so the 0, 0 coordinate would be here. And in capital C, this pixel contains the sum of all the values in this outer rectangle. We are, however, interested in the values or the summation over the pixels within this smaller rectangle. But we discussed that if we had computed this one, the values within this smaller rectangle are basic, or the sum of the pixels contained in this smaller rectangle is the sum of the pixels in this larger rectangle minus the sum of these pixels minus the sum of these pixels, and since we have subtracted this one twice, we have to add it again, and this is expressed in this equation. And there you have it. If we could compute this, we can compute what we are really interested in terms of 1, 2 subtractions and 1 addition. Of Of course, there are more additions and you know, this is fast for any computer to do. So indeed, the effort of computing something that has to do with the sum of pixels contained in a local rectangle or window neighborhood, however you want to name it, can be done in constant time if we have done some smart pre-processing. That is, we have created an intermediate result. Of course, this is only worthwhile if it is not too expensive to create this intermediate result. And so we asked the question, how to compute these images capital C that contain for every pixel, say this one, for this pixel, capital C would contain the sum of all the pixels to the left and on top of it. Right? How to do that efficiently? We saw that we can resort to dynamic programming. In this situation, we want to compute the value of capital C at this pixel here. And that can be done using dynamic programming. So basically, we would have to, in order to compute the sum of all the pixels in here, well, we have to add the value of this pixel. And we already know the sum of all the pixels in here. We did that some iteration earlier. So we add this to the value contained here, value in C at this point, which is the sum of all these pixels, plus the value of capital C in at this pixel, which is the sum of all these pixels. And now we have added a certain region twice, this one here, right, is contained in both of them. So we have to subtract it again. So that is when we compute these integral images, these capital C images, we have 2 additions and 1 subtraction for every pixel. And again, we see that these images capital C can be computed in constant time per pixel. Of course, we always have to iterate over the image, where we have to do something for every pixel, but what we are going to do for every pixel is something that does not depend in any way or form on certain other parameters. Yeah?
The pre-processing part itself will take O of n cross n, like it will be a polynomial time, the pre-processing. And then while we are running the algorithm, then it will be constant.
What is polynomial here?
The pre-processing part, like when we are actually calculating the previous values.
Yeah.
Let's say C, X, Y at any previous index.
Yeah.
So that pre-processing part?
So, the blue thing here indicated we have already iterated over that. That is, we have computed this for here, 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 here. For all of those, we have that already computed. Right? Now we want to compute it here. That is, what we want to compute for this pixel is the sum of all the pixels in here. But we already know the sum of all the pixels in here, because at some earlier iterations we came across this pixel. So the value here is already given. And this contains this sum. The value here was the last thing we computed, and this contains this sum. So to compute the value here, we just add the current sort of pixel value to this sum and to this sum, and then subtract this one here, the thing we have added twice. So there is no polynomial complexity in here. It's constant. Right? This is called dynamic programming, because for every xy we are currently considering, we reuse earlier results. Right? We have them. We do not have to compute them again. Constant time. Extremely fast. Slow in Python. Because this is still, we have to iterate over all the rows and all the columns. We have to visit every pixel to compute this. But in any compiled language, this is more than real time. This is ridiculously fast. And this is what your cameras do when you take pictures of people, and the camera just, shutter just opens once people are smiling. How does the camera know that the people it is focusing on actually smile? There is software built into your cameras. It's burnt onto the chips already that detect faces, and once faces are detected, it is rather easy to determine whether the mouth is closed like so or opened like so. So the cameras can do that, and they couldn't do that 14 years ago, but 14 years ago there was this breakthrough in computer vision where two guys called Viola and Jones came up with this idea to compute certain features. We'll study this Viola-Jones algorithm in the next semester. We'll see that these ideas of dynamic programming are at the heart of many modern image analysis algorithms. And why? Once again, because it is so fast. It is so fast that a consumer product camera can do it without you having to wait like for 5 seconds or whatever. Hey, okay, these two slides, this one and this one, summarize the fact that local averages means not the Gauss, not the weighted ones, but constant average, like when we have just sort of a constant weight. These things can be computed in O of 1. All right? And I promised you that we will now study the idea of the median once again and see how those can be computed quickly. So, and I brought you a better example, right, than last time. Let us briefly recap. What does the median filter do? We, again, are given an image f, say this one, which is distorted by salt and pepper noise. And for every pixel in this image f, we, again, consider a local neighborhood that is surrounding this image. All the pixel values surrounding the current pixel are collected in a set nxy. And then we order that set nxy. Right? And we order it in an increasing or ascending fashion. So given nxy, we turn it into a set rxy, which is just all the values in xy, but now ordered. It's an ordered set. And the element right in the middle of this ordered list or set, list is probably the better name, of pixel values is called the median. Of course, this does not only hold for image processing. This is a very venerable statistical technique, but the center element of such an ordered set or list is called the median of the values in this neighborhood nx, y. And then if we are going to compute a new image, g, where at every pixel xy, we simply set the median of the pixels in the nxy neighborhood in f, we obtain a median filtered version of f. And here you see the power of this idea. We have this image that is distorted by noise. It's salt and pepper noise, so we have white pixels and black pixels. And here we have a version of the image which I filtered using a 3x3 median, so a very small, very, very small neighborhood. Contains just 9 pixels. The noise is gone. It's perfectly gone. Right? And this is again due to the property that these median filters, in a sense, do a local majority voting. If there is a neighborhood with more darker than brighter pixels, the median will be a darker value. If the pixels in the local neighborhood are rather bright and there are just a few dark ones, then the median will be a rather bright pixel. This is sort of a majority filtering process. And because of the characteristics of this salt and pepper noise, for instance, like, can you see this white pixel here? It's an isolated white pixel in a gray of sea of gray. So it is an outlier. It is an outlier, and it will go away by median filtering, because the majority in this local neighborhood here is gray, so the median will be something gray. This white will be set to something gray. It does not suffer from outliers as a mean filter would. If we were to compute a mean filtered version of this image, we would remove the noise in this extreme form, but we'd still see, you know, remnants of it, because mean filtering computes averages which may be distorted by very large or very small values. Okay. Well then, how do we do this in practice? Let's see. We want to compute the median filtered version of an image. And let's call this image F, and let it be of size m by n. So we have m rows and columns. Of course, we do have to iterate over every pixel. This is something we always have to do in image processing. There is no way about that. Usually, we have to do something for every pixel. So these two outer for loops will always be there. And then I say sanity check for x and y, which is my way of saying I don't care about what happens at the boundary. Right? Usually we would have to have some if x minus m over 2 like, is greater or equal than 0 and less. This is, you know, sanity check. This line is for you to replace by whatever you want to do around the border of the image. Okay? But of course, you are not allowed to do, say, these kind of things here. You are in a certain pixel x and y, and you add or subtract something from it. And if that what you add would lead you sort of outside of the image, then, you know, things get nasty. So make sure that does not happen. Sanity check. How you handle it is to your liking. So you have to replace that by whatever you do. Usually, you'll have if clauses here. Right. If this is okay, then do it, otherwise do nothing. Once we are sure that we are considering a pixel that is where we can securely compute these kind of things here, we initialize this set, which will contain all the pixel values in our local neighborhood, to the empty set. And then there are these two inner for loops, where we iterate over all the pixels contained in this local neighborhood. Right? And for simplicity, I always assume that these m and n are odd numbers, so that there is a clear-cut center pixel for every neighborhood, but we don't have to get back to that. Now, we iterate over all these pixels and increase this set by every pixel we find in the neighborhood, by every pixel value. And then we call quicksort to get this ordered version of this set, and then we determine the center pixel of this ordered set and set it as the new pixel value in the output image G. There you go. That is how you compute a median filter. And well, so the effort per pixel is of course determined by the size of m and n. We have these two for loops, right? And when I say the average effort per pixel is q times log q, I actually already ignored this here. I don't know why I'm ignoring that. I should probably include it, but you know, I don't. This is the effort of this operation, right? Because sorting can, and this is extremely important, be done on average in q log q, where q is the product, is the size of the local neighborhood. Q log q looks good generally, like, you know, it's better than quadratic. It's not quite linear yet, but that does not look too daunting. Right? But if these mask sizes, the sizes of the neighborhood we want to compute the median for, increase, that is, if this q becomes large, then all of this becomes tedious. It's not fun anymore. You have to, I don't know, start it, go get some coffee, come back, see if it has finished processing, Maybe it even has not yet. So this is not a good idea. Not a good idea. And this is why I call it a naive implementation. Well, naive is a strong word. This is, of course, what everybody does when they're told for the first time, well, implement a median filter. This is what you do, obviously, sort of. Can we do better? And here is an extremely deep insight from statistics. Why is this median what we call a robust statistic? There is another fancy term for the median. It is the 0.5 quantile of a distribution. Let me explain that. What we see in the upper panel is a probability distribution. Some probability distribution. I don't care. It has 2 peaks, apparently. I don't even know where the mean value of this thing is. I don't know. This is some one-dimensional probability distribution. And in the lower panel, we see the cumulative density function. That is, at every value x in the lower panel, we actually look at the value of the integral from here to wherever we are here. Right? And if this is a true statistical distribution, then the cumulative density function will be something that approaches 1. So if this goes all the way to infinity, then it will have a value of 1 out there at infinity. If it is truncated, it will reach 1 prior to that. So this interval on the y-axis in this lower image goes from 0 to 1 somewhere. So somewhere on this interval is 1/2. Now then we draw a line from here until we hit the blue curve. Once we hit it, we go down here, find an x, and this x is the median of the probability distribution. That is actually another way of defining the median. If you think about it, so we have been discussing it for discrete distributions, like discrete collections of pixel values. You can think of them also as seen in a second, statistical distributions. And if you try to map this onto what we have been discussing last time, you'll see that yes, it is true. So the median is the 0.5 quantile of a distribution, which is to say the median is the point at which the cumulative density exceeds 0.5 or reaches 0.5. And to understand what is to come next, we so briefly have to look into the idea of histograms. Usually I don't discuss them because I always assume everybody knows what they are, but let's ever so briefly discuss them. Histograms count things. And let's be specific with respect to our application domain. Here is an image. It consists of 265 by 256 by 256 pixels. Those pixels are gray value pixels. That is, we have 256 square numbers between 0 and 255. That is, all the gray values in this pixel image will have a value either between the 0 and 255. Okay. Apparently, certain intensities are more frequent in this image, so there's lots of gray here. The gray is something, 128, I don't know. So what I have plotted here is I have counted for every possible pixel value, for every possible intensity in this image, which again is bounded by 0 and 255. It's possible to have an intensity of -50. And it's not possible for this image format to have intensities of 3519. Right? It is bounded. And for this interval, I have counted how often is there a pixel of, say, value 50. Right? I have counted this for every pixel, and then I have computed the sum of all these counts, the total amount of this value, 256 squared, and divided these counts by 256 squared. This is why we have fractions here. Right? I have turned the histogram into a probability mass function, because if we add these things now together, we end up with 1. We see this here. Right? This is the histogram, normalized histogram, and then this is sort of the probability density, cumulative density we saw earlier, but now for a discrete distribution. Right? We will not whatsoever study statistics and these kind of things in this course. Those of you who have been with me know that I am doing a lot of statistics, but not in this course. So this is a discrete distribution. This is a discrete cumulative density. And let's see, so here's 0.5, we go here, and apparently the median value of all the pixel values of this image is something about 128 something, I don't know, 170, this is like, can't read it there. But it is something gray, and that makes sense because really the majority of pixels is gray. We can actually see that with this peak here. These are histograms, right? And whether we compute such a histogram for a whole image or just a sort of local neighborhood, doesn't matter. Histograms count things. In our case, they count pixel intensity values. Now, here is how we could improve on computing the median. This is an algorithm that was proposed by Wang in 1979. You see, these things were important already decades ago. The first 3 rows are just as in our previous example. We iterate over all, then we make a sanity check. And then we check if we, sanity-wise, say that would be this pixel if we are lazy, are in the upper left corner of where we compute something. And we then initialize a histogram. That is, we allocate some memory and set everything to 0. And then we begin counting. That is, we iterate, and this is funny, so basically for the first pixel we begin to really compute that. For the first one where we pass the sanity check, we really compute the histogram of, say, in our case, these 9 pixels here for this pixel there. Right? And then we move a pixel to the right. And what we do then is sketched here. Let's say we have done that already, but here, at the very first time, we compute the histogram over the neighborhood we are dealing with. And for every other pixel, we then do the following. Given the histogram we had here, we remove, in our case, 3 pixel values from the histogram. That is to say, for instance, we would, I don't know, remove 1 pixel, one here, 1 there, and 1 there, because those were, say, the 3 intensity values in this little column here. And we have to increase our histogram again by 3 pixel values in our example here, namely those 3. Right? So what happens here is, at the very first time we can actually compute something, we really compute a histogram. And then we begin moving this mask, but instead of computing a full histogram at every pixel, we just remove, in our case 3, but depending on the size, n values from the histogram, and add n values to the histogram. So we have this subtraction of a couple of values from the corresponding bins in the histogram, and we have to add some values to the corresponding bins in the histogram. And then we determine this 0.5 quantile, right? And then we're done. We have computed the median for, in this case, this pixel here. Now, what is the computational complexity of that? Here I'm actually counting the sort of height of the mask. So we have to iterate over, in our case, 3 pixels. This is that, O of n, 3. And I am assuming that we are talking about gray value images here. And that is to say, if we are computing this here, well, you know, the histogram contains 256 bins, and we have to do some summation over these histogram things. So at max, we would have to do 256. That is if the median is actually 255. It can happen that all the pixels are white, and we have to go through the histogram. Let me show that. So, oops. Okay, here in this for loop, we iterate from 0 to the number of colors, that is size of the histogram. In our case, it's this. So we have one loop, say from here to it. It may terminate early if we exceed the 0.5 quantile, but it can happen that we are dealing with a situation where all the pixels are white, then we actually have really to iterate from here to here, and then, okay, the median is 255, right? So worst case scenario is that this for loop goes over 256 iterations if we are talking about intensity values. But 256 is something that is always 256. Right? This does not depend on the size of your filter mask whatsoever. This is O of 1. Here we already see sort of the danger of talking about O of 1 because we are lucky that it's a small number. It's a rather small number, but you know, it requires us to do something, but it is constant. It's of constant effort with respect to mask sizes. This is not influenced by the mask size. So this iteration is O of n. This iteration is 256 operations is O of 1. Together this is O of n. It looks good, right? It's better than Q log Q. There's no sorting here anymore. And the reason that we can get rid of the sorting is the observation that the median is the 0.5 quantile. I promised you to do that in O of 1. Now we are not there yet, obviously. Right? This is O of n. It's already quite okay, but still depends on the size, or at least one dimension of our filter mask. Okay. But note this. If we're given 2 sets, now very abstractly, two sets, say, let's be specific then. 2 sets of intensity values, A and B, and the histogram of their union is the sum of the 2 respective histograms. Verify that at home. It's a beautiful property of these kind of counting processes, right? Check that out. And here is now an idea, and I told you last time, we discussed it ever so briefly, that we typically have a trade-off between speed and memory consumption. If we need low memory, then it's typically rather slow, whatever we are doing. And if we are really fast, then usually our memory requirements grow. And this is what happens here, because in this algorithm, we have to have one histogram, you know, which we adapt locally, but it's just one histogram that has to be updated all the time. And now we will have a histogram for every column in the image. So memory explodes, memory requirements explodes, but everything will become very, very fast. This is, and look at this, this is Perrault and Hébert, 2007. So this is basically yesterday. It's so crazy to you know, wonder why it took so long. But you know, whatever. This is how medians are computed nowadays. We iterate over the image, we make sure that everything is fine, with respect to boundary conditions. If it happens that we are in the uppermost row, for every pixel in the uppermost row, we initialize a histogram for every column. At the beginning, there will be just in those histograms just the value for these pixels here, and for the others we don't know what there is, but we have at least, you know, sort of allocated memory already. If we are at the first sane pixel, then we also initialize a histogram that contains the values of the neighborhood which we are interested in, the neighborhood size we are interested in for this one. And now, we move one pixel, let's say we were here, and this doesn't matter where we do that. We were here, and now we move here. What happens is that for the histogram of this column, we sort of will now remove the value that represents the pixel intensity at this pixel, and add the intensity at this pixel. So we update our histogram for this column. And once we have done that, we will, as we did prior, remove all the values here from the local histogram and add all the values here to the local histogram. Now we have two sort of histograms we need to update. We have the column-wise histograms, which will be updated whenever we move one step, we update them. And we have this local histogram, which we are interested in maintaining. And so this has to be updated just as in the case before. And here is the effort that requires. We do assume that, again, we're talking about grayscale images. We have, after this has been initialized, and so for every pixel other than this one, the first sane one, which in this case is like this 3x3 mask is the first thing, we have to do one subtraction and one addition to one of the histograms we have initialized. That is this here. And then we have to, remove the three values sort of in this column here from our current histogram and add these three values. And this is again something of this complexity. And so basically from our current histogram we have to subtract the histogram and add some other histogram. And there you are. And then we have to compute the quantile, which I blocked out. So this s equals 0 dot 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 is, whoops, is this here, right? Which I was too lazy to repeat. And we have to do this. And all of this is independent of our mask size. Right? So this is indeed mathematically of effort O of 1. Right? And saying that something is of effort O of 1 is good and well, but in practice, O of 1 can still be expensive. However, they pushed the complexity to O of 1, which is not to say that this happens instantaneously, because there are still a lot of for loops involved here. And they are hidden in these sub-add and these dots here. Now, however, large constant factor, that is to say, even though this looks really, really cool, it is very cool, but it still requires some computation, and that can be slow if it's done naively. But Perrault and Hébert didn't stop here. They actually made it really fast. For instance, instead of these histograms we have discussed, you can think of hierarchical representations of histograms. You can count how many pixels are of an intensity less than 128 and higher than 128. If you're dealing with a pixel that has an intensity larger than 128, you don't have to do something with the part of the histogram that is less than 128. You just sort of iterate over the upper half of the histogram. This is multi-level histogram, so they, you know, neatly reduce the effort. And then instead of adding and subtracting things, they actually, I'm not saying you should ever do that yourself, realize these things in terms of bit shifting. If you compute or program in C, this really will be very, very fast. Very, very fast. It doesn't make a difference for Python. But bottom line is, it is O of 1, and by very, very advanced programming techniques, you can make it fast. And it is actually contained within OpenCV right now. So if you use OpenCV in this context of image processing and computer vision, the median filtering function provided by OpenCV is an implementation of this algorithm we just discussed. To wrap this up, we have seen that mean filtering can be done in O of 1, and we have to do some we have to compute intermediate results, these integral images, which can be done by dynamic programming. So that is like in imperative languages such as C, compiled languages, very, very fast. And then mean filtering becomes a problem that can be done in constant time per pixel. And then we have seen that if we sit down and think about what the median really is, say the 0.5 quantile of a statistical distribution, we can make use of that to avoid sorting and just sort of maintain histograms, which are discrete statistical distributions, maintain histograms and avoid more complex computations. And if we actually update these histograms in a very smart way, the effort for median filtering, which is a non-linear filter, can also be pushed down to O of 1, and then by very advanced programming techniques be actually made very fast. What about filtering with, say, a Gaussian? That is neither a non-linear operation. It is a linear, we saw that, linear operation. And it's not a naive mean filter approach, but a weighted filter approach. Can we get that down to O of 1? Yes, we can. And we will study that next week. And it turns out that this is really, really possible, but that again requires advanced thinking. And so we'll study the problem of how to do Gaussian filtering in O of 1 next week. Right now, since we have been talking about nonlinear filters, we will continue down this road, then move back up again next week. Talk about extremely efficient Gaussian filtering, which is, I haven't said it, but among all the filters we have discussed so far, the median is more important than the mean, and the Gaussian is probably more important than the median. It's used more often, and so it's good to be able to do that fast. We'll study it next week. Now, let us continue with our discussion of these non-linear filters. And there is a topic that is called morphology. And it's basically the same thing we just studied in the case of median filtering. We're given an image, and for every pixel in this image we have an ordered set of the values in a local neighborhood surrounding that pixel. So this is exactly the same we saw earlier. And we are then considering the operation where in the new image we set the pixel at x and y to the smallest value in the ordered set. Right? When we talked about median filtering, we had this RQ minus 1 divided by 2 here, which was the center pixel in the ordered set of pixels. Here, we're actually interested in the smallest pixel, that is the leftmost pixel in this ordered set. If we do this, this operation is called erosion. Now, if we go for the largest value, that is, we have ordered the pixel values, the intensity values in the local neighborhood, and now we are interested in the largest value and use that one as the value in the new image we are computing right now, then this operation is called dilation. And here is what those do. This is typically of considerable importance in binary image processing. Here is a binary image. A binary image is thought to be something where pixels have values of 0 and 1 only, binary. And in this visualization, I do assume that the black pixels are those of value 1 and the white background pixels are those of value 0. This is of course not the case. The image that I am including on the slide C has lots of pixels of 255 and lots of pixels of 0. But conceptually, I treat it the other way around. Right? Black is 1 and white is 0. No problem there, we can do that. This is the original image, and here is an eroded version. What has happened? Can you see why it's called erosion? Yeah, it's smaller. It's, for instance, like here, the ear things, they are sort of, gone. Why is that? Because here's a single pixel, right? And if we just go for a very small neighborhood of this pixel has value 1. This black thing is 1. Everything else here is 0. Here's some other ones. We sort the pixel values in this neighborhood. The minimum is 0. So we set it to 0 here. And that obviously, leads to this image sort of being shrinked a bit. In particular around the boundary of this shape. Binary images are also called shape images. Dilation does the opposite. Right? This one is sort of a bit bloated, inflated. And why would that be of importance in binary image processing? Can we do something with that? Let's see. Here is the original shape image. And then I have computed the eroded version. And I have subtracted this from this. F minus E of F gives this. Isn't that cool? So, well, yeah. It indeed is cool. This is not, it's a funny thing. You can try that at home. I mean, now you know how it's being done. But you can try it at home sort of naively. How would you, given something like this, isolate the pixels on the boundary? Is not necessarily trivial if you think of it. If you want to try to come up with a solution. And then you realize, this works. So here we see an application of erosion. It allows us to extract the boundary of a shape image. It turns this into a outline. It gives us the outlines of a shape image. The operation where we first erode and then delete, this is called this composition of two functions. We first do this and then do this. This is called opening. And if we switch the order, that is, we first delete and then erode, then that is called closing. And here's what that does. Here is the original image, and here is the open image. Let me see which one is more interesting. Let's look at the closed one, because that is it. See that there is sort of this dent in the right leg of the cat. Here, this black, white, black. This tiny white dent is gone here. Because what I have done here is I have first deleted the image. That is, this is the original image, and then I have computed this, and on this one I have computed this operation. And so closing, if there would have been a tiny hole in here, that would have been gone, because first we delayed, the hole is being filled, and then we erode, but once the hole is filled, there is nothing to erode in here anymore. So this can be used to close holes in shapes. And it can be used to close like small gaps along the boundary of something, if that is of practical use. So in a sense, this shape here looks smoother than this one. Let me see if I have one more. Yeah. Okay, let's stay with this one. Now, this is of tremendous practical value, right? And indeed, we had a project running for a couple of years now where we did image analysis of images that were recorded with cell phone cameras. Pictures were taken of plants out in the field, and we were trying to automatically determine if the plant was suffering from some fungal pathogens, like if there was a fungus or some disease infecting the plant, and there were like tiny spots on those leaves, and we had to isolate the spots and then to analyze their characteristics. And actually in doing that, we used a lot of morphology. So these operations are called morphological operations. This is of tremendous practical value and importance. And but this is all there is to it. This is all there is to it. This can also be generalized. I'm just showing examples with binary images, but you can also do this with intensity images and whatever. And there is a whole community out there of people who are studying this, and for some freakish reason, many books on image processing spend at least a chapter on this. I don't understand that. I don't understand. Like looking at these 4 slides, we're done. This is, really, this is just, we discussed median filtering is by far the more important thing. We understood the idea of let's sort local pixel values, and then we saw what happens if instead for the middle value we go for the smallest and the largest. Done. We don't have to study morphology. And please don't be fooled into believing that this is more important than it really is. It is not. Many of the books spend way too much space on this stuff. It's very practical, of practical use, but this book, if you really want to know everything, go on, read it. It's not worth it. Believe me, it's not worth it. Sorry if you watch this on the internet, I have to say so. It's true. I can be opinionated about things, and why shouldn't I? Let's move on to something else. This is called bilateral filters. This is again something that is rather recent. First time it was discussed in detail was in 1998, Tomasi and Manducci, and I guess the current standard text on this is probably this paper by Paris, Kohn-Probst, Tomlin and Durand. Bilateral filtering theory and applications appeared in a journal in 2008. So again, 1998 is not that far away. It's actually, I remember that year. Let's, again, without further ado and without going into the details, the headline is still nonlinear filters, right? But it looks as if this is just a convolution for which we found that convolutions are linear operations, right? So we are given an image, and we are given a pixel, which is the center pixel of a local neighborhood. And the coordinates of this pixel are p, that is x, y. Right? And we do also have the coordinates of all the pixels q in the local neighborhood. It's different terminology. I have used this terminology because this is what they use in the literature. But again, we have a center pixel at x and y, and pixels surrounding this pixel at corresponding locations in a neighborhood of this center pixel. And if this thing here, oops, was not there, this first factor, then this is Gaussian filtering. Because this is supposed to be a Gaussian convolution mask, and this is the value at q, and this is just the convolution of this thing with that one, because if you sit down and meditate about this equation and mentally remove this factor, you see this is convolution. But the headline is nonlinear filtering. So I would not have listed it here if it was a linear filter, and it is not. And this is because of this term here. And what this bilateral filter does is, let's mentally abstract away this one for a second, but just go for this one. P is our center pixel, and this is the sort of distance from the pixel we are summing over all pixels in the neighborhood. This is the distance between the pixel we are currently considering and the center pixel. And we put this distance as the argument into a Gaussian distribution, which is sort of, it gives us a weight. Right? This is a number between 0 and 1, and mostly slower, likely slower. So this is just sort of a weight, and we weight the contribution, the intensity value f of the current pixel with respect to its sort of distance to the center pixel. This is Gaussian filtering. And it's weighted average. The weights are given by this function. And at the same time, and this is what makes this very, 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 very different from Gaussian filtering, not only do we have this weight, but also this weight. And whereas this here is just sort of the distance to the center pixel, something we studied earlier, this here is actually a weight derived from the intensity difference between the center pixel and the one in the neighborhood we are currently computing. So we have this weight times the value, which would just be Gaussian convolution, but then we also have another weight. And we multiply that into this weighting scheme as well, and this destroys the linearity of this operation. This is anything but linear. This 1 over WP is basically the sum over these products for every pixels in this neighborhood. So when I implement this, I first compute this, and then for every pixel I compute this product here, add that to some variable, and once I'm done, I divide by the overall sum of these two factors. This is a bilateral filter. What does this thing do? This is easy, or well, quickly to see. Here is an image plotted as a function. You remember that we plotted asterix and obelix as a function very early on throughout this lecture. Apparently, there is an edge in the image, right? Something goes from sort of lower intensity values to higher intensity values. And the whole image is noisy. And we want to get rid of the noise. And this is the result of bilateral filtering. And we see that the noise has gone, but the edge is still there. And this is actually a visualization of the bilateral filter used at this pixel here. there's a certain, here this one, can you see it? So within this, all these pixels, I'm singling out this one, and this is the shape of the filter. This is how this thing would look like if I plot it as a function at this point. And you see it is a Gaussian, but it is sort of truncated. And this cutoff comes from here. And this cutoff is different depending on where you are in the image. And therefore it is not linear. If this was a usual Gaussian, then it is independent of where you are in the image. But this thing will look different at every pixel in this image. Well, not so much, but in a usual image, this will look different at every pixel. Because this factor here will be different for every local neighborhood, basically. And so this is what this bilateral filter does, is it basically does Gaussian smoothing, but it preserves edges because it also looks for differences in intensity. And to appreciate that, here is what the Gaussian filter would do. Can you see the difference? This is what the bilateral filter does, and this is what the Gaussian filter does. It removes the noise, but it also removes the sharpness of the edge. Because the Gaussian filter computes local weighted averages. And so for a pixel here or here, the local average also depends on these and these pixels. And this illustrates the fact that averages may suffer from, well, outliers or certain extreme variations in a signal. Right? That is, the pixels in say, this band here, they are being sort of smoothed. Their values are being smoothed. You know, if you use Gaussian filtering, then it is also called image blurring. It blurs the image, and here we see why that is. Because Gaussian filtering destroys the sharpness of edges. Bilateral filtering preserves that. Unfortunately, this is a really expensive operation. There is nothing you can do to make that efficient. There are hacks, and if you, I don't know, Google for it and read about it, people have proposed approximative bilateral filtering, but this is a nonlinear operation for which, to this date, nobody has come up with a more efficient way of doing it, like than, you know, computing it naively. It has beautiful properties of smoothing sort of rather constant parts of the image, but preserving edges. Here is an example. This is actually taken from the Tomasi paper, I guess. Yeah. So depending on how you choose the two parameters of the two Gaussians, rho and sigma, you get different results. If you want to, you can destroy edges. Right? But if you don't want to, you can preserve them. How to choose them? I don't know. Actually, I have to be very honest with you. When I created these images, I had to play around for like 15 minutes until it looked nice. I should not have said it, but this is the truth, and it's important that somebody tells you the truth. Really, you know, I created these pictures, and it took me some time until I found the rho and the sigma that, you know, gave results that were okay. Is there something you can do about it? No. This is very, very, very sad, or I'm sorry about it. I have to tell you, it still very much depends a lot on experience. And you can only gain this experience by getting your hands dirty and see what happens if I make this large and this small, and then once you have done it for the first time, you remember it the next time. So this is all based on experience, unfortunately. All right, let's learn something else. Now, we have seen what happens if we erode an image and subtract the result from an original image. Right? that is in the context of binary image processing. We saw what happens if we apply a filtering operation, and erosion is just another kind of filter, to an image and subtract the result from something we're given. Now we can do the same with Gaussian filters. What we are given here is an image and we convolve it with a Gaussian. So we blur it, all right? And this blurred image I call S. And I don't know why I switched to parentheses rather than brackets, but it doesn't matter. By now you should be used to my, switching notations. Given an image, we blur it, the result is called S. And then we compute the difference between the image we were given and the newly created blurred version, and this is called R, like as in residual. And then we compute the final image. This is called F tilde now, and I don't know why it's not called G, but whether it's called F tilde, it doesn't matter. And F tilde results from adding this residual we just computed, sort of scaled or weighted by a factor alpha to the original image. And if this alpha is set to 1, then this process is called unsharp masking. And if it is set to something larger than 1, it's actually called high boost filtering. And I should have brought you an example of high boost filtering, but this is unsharp masking. Can you see a difference between the original image and the unsharp masked image, or unsharp masked image, whatever? Do you see a difference? Is this probably sharper than this one? It's not, but it should be. So have a look at the slides I will upload. The image on the right is much sharper. Local contrasts are higher. This is a way of sharpening an image. Here is the original, here is the blurred version. This is the difference between the original and the blurred version. And of course, this difference is large where there are sharp edges in the image, right? Because if we blur the image, these sharp edges will go away. So the difference between the original image and the blurred image is basically at the edges. Now, if we add those edges back to the image, I probably should have indeed gone for high boost filtering like 10 times, then it would really be crystal clear. So this is a way of enhancing the sharpness or contrast of an image. And it depends on Gaussian filtering. Will we study it any further? No. Here is something that we, again, will only ever so briefly cover in our lecture today. But this will come in very, very handy in the next semester. So, and since we are talking about lots of filtering operations anyway, I thought, well, it's a good place and time to discuss it today. Look at this. We are given two Gaussian distribution, two Gaussians. One is red and one is green. And we compute a difference of Gaussians by subtracting the one from the other. And this gives us this blue curve. This is obviously the green one subtracted from the red one. This thing here also goes by the name Mexican hat. Can you see why? It looks like a sombrero in a sense. Probably shouldn't call it like that. It used to be called Mexican hat function. Okay, difference of Gaussian. What would you say will happen if we use, this is just a 1D example, but of course we can do this for two-dimensional Gaussians as well, if we use this as a convolution mask to filter an image. We use a difference of Gaussian. Here we go. This is the original. here I have used a difference of Gaussian where the first Gaussian has a sigma of 4.5. So the first Gaussian in this example is more narrow because the sigma, the variance parameter, is smaller, and the other Gaussian is wider because the variance parameter is larger. So here I have subtracted a Gaussian with a variance parameter of 9 from a Gaussian with a variance parameter of 4.5, and I used the resulting function to convolve the original image, and this is what we get. It detects what? Edges. It detects edges. And if when I increased the variance parameters of these Gaussians, it still detects edges, but things become more blurry. Right? But note that it not only detects edges, but also in a certain sense, those parts of an image that are small homogeneous parts, like as my mouth here. This is sort of visible in this representation, in this filtered version. It's also visible in here, and here you can actually see my pupils, and they are sort of rather dark blobs here. So this operation of convolving with a difference of Gaussians sort of identifies locally homogeneous regions surrounded by something else. Why is that? Because everything that is very far away from the local pixel we are currently considering is being multiplied by 0 anyway, right? Everything that is very close to, say, the pixel we are currently considering gets a high weight, and stuff that is not very far away but also not really close gets a negative weight. So this is, this is indeed again this difference operation we discussed when we talked about gradients. This is somehow subtracting something from something else, and well, it has a certain width. So certain pixels. Let's go to the image. Let's say we are here and we look at a local neighborhood. Then everything that is very close to the center will get a positive weight, and everything that is not so close will get a negative weight, and everything that is far away will be 0 anyway. And so if the region in the image we are currently working on, when we iterate on that, is rather homogeneous, then these rather homogeneous parts will all get a positive weight, everything else will be subtracted. So not only does this do edge detection, it also sort of, depending on the size, let's call it region detection, is probably a bit saying too much, but it finds locally homogeneous parts. Okay?
I have to speed up.
So those were difference of Gaussian filters. And we will now talk about the Laplacians. And let's consider a one-dimensional signal consisting of lots of zeros, and then there is a -1 and a 1 and lots of zeros. So it's a one-dimensional image. And we convolve this image with this kernel. That is, we slide this below here and compute these local values, as we discussed, when was it, last week or the week before that. And I point out that this is convolution, not correlation, so when you do this, you have to flip this, okay? So mentally flip it. And if we, therefore, compute the convolution of this signal sort of with itself, right, because, -1, 1, -1, 1, rest is 0, we get this. We get this. One-dimensional example. And this again looks like a differentiation operation, right? It is just as we discussed. Now there's a minus here, but it could be a plus and a minus here, it doesn't matter. I could multiply all of this with -1 and with 2 here and -1, -1. It's not the case. Anyway, we can think of this as a differentiation. And so therefore, we can define a discrete differentiation, or an operator that does differentiation of discrete signals, as the convolution of the function with this thing. And remember that when we talked about this example of, you know, let's understand images as functions, and let's think about gradients of functions, and we talked about derivatives, and somebody had a great question about why I didn't divide by 2, and all these things. And I said, you know, there are many other ways out there as to how we can define these operations that do something like differentiation for discrete signals or functions. So we can understand the convolution with this mask to be a differentiation. Now then, this is the first order derivative. Well, if we do it twice, we should then get the second derivative, right? And this is actually what has happened here, right? We have, this is the convolution of this signal with this mask is what's happening here. So we see that I actually was ahead of myself. This is already the second derivative. But so convolution with this thing is derivative. If we do it twice, we get this, which is the second derivative. And now, why then would I have talked about Laplacians? If we are given, now again continuous, let's remember what we know about calculus, function f of x and y, and there is an operator called the Laplace operator, which is basically the divergence of the Nabla operator, which is also written as Nabla square, and we discussed that in one of the first lectures. Long story short, this is the definition of the Laplace operator. It is the inner product of Nabla square and the function. So here you have it. This is called the Laplacian. And if we were to use what we just learned about the second derivative of a discrete signal, we can think of it like that. There are other ways, but this is one way of thinking about the second derivative, convolution with this mask. And we do this for two-dimensional functions. In the example prior, it was just one-dimensional, right? But we can do this with respect to the x-coordinate and with respect to the y-coordinate. And then, of course, given the definition of the Laplace operator, we have to add these two things together. And if we do this, we get this. Okay, so we have the second derivative with respect to x, second derivative with respect to y. We add these two results together. It's that what we get. And this can be understood. Look at it. So we have Laplace of f at x and y is x minus 1y, fx plus 1y, xy minus 1 plus fxy plus 1, and then 4 times the center pixel. This is what these two equations say. We can understand this as convolution with this mask. Okay? And that is to say that, again, the Laplace operator can be computed. The case here of discrete functions, digital images, can be computed as convolution with this mask. And all this goes to show that what I told you at the very beginning of our series here on image processing, that there are so many different ways as to how we can compute derivatives of images and whatnot. Now we have seen other ways. Right? I announced them earlier. I said there are things that are called the Zobel, Kenny, Previtt, Roberts gradient, blah, blah, blah. So many different things. Don't be alarmed if you read something somewhere, either in a textbook or in the literature, and it says, yeah, we, I don't know, compute a derivative, here's how it's what? I've never seen this before. May happen. Right? Because it really does not really matter. As long as it is consistent, it's okay. But it can be something you have never seen before. You look at it, they claim it's a derivative, you think of it, yeah, it makes sense, then it's okay. If it doesn't make sense, it's not, but usually it makes sense. So there are many, many, many ways of how these things can be done. And again, since the Laplacian has to do with the second derivative, depending on how we choose the first derivative, the Laplacian may look different. It's important to know. It's a very interesting operation to compute the Laplacian of an image, because again, it is, as we just discussed with the difference of Gaussians, sort of a blob finder or an edge emphasizer. Let's look at this again. Where with the Gaussians, the center thing was large and the surrounding things were small. The Laplacian is the other way around, but you know, it's just multiplication by -1, doesn't make a difference. The center will be emphasized, everything surrounding it will not so much emphasized, that everything that is further out, you know, will not be considered anymore. So this is a way of finding edges. It is a derivative, second order derivative, and if the image or the signal, say, we are dealing with is you know, noisy, should be constant, but there is a noisy pixel or whatever, these derivatives will be very sensitive to that. Right? Because whenever there is a change in the signal, those derivatives will give us a large value or a comparatively large value. But maybe that short peak should not be there, it's just salt and pepper noise, whatever, right? Shouldn't be there, it's maybe just noise. So derivatives are used to detect edges, but if there is noise in the image, they may confuse noise for edges. So this is not desirable. And therefore, what you will typically do is, if you're given an image and you want to use the Laplacian for edge detection, say, you first smooth the image with a Gaussian. And all these, all our discussion at this point in time already is beginning to hint at the importance of the Gaussian. Right? Why is there no Millian here? Right? Why the Gaussian? Because when we, I don't know if we actually made it explicit, but convolution is a linear operation. That is, it is associative. It doesn't matter if I convolve L with the result of convolving G with F, or if we first convolve L and G and then use that as a convolution mask for F. Right? So we can set parentheses here as to our liking. Doesn't matter which of these two things we compute first. And so therefore, we can think of computing this first. But we know that this is a very sort of familiar function, and it's actually rather simple for us to compute the second derivative of this thing. And it's really rather simple. So it's actually this. And which is to say, instead of carrying out two convolutions, we can probably compute just one convolution with something we can pre-compute using pen and paper. All right. So there you have it. This is an edge detector that is not so sensitive to noise. The idea is, once again, to use the Gaussian to remove noise, and then to use the Laplacian to detect edges. But we can apply the Laplace operator to the Gaussian right away. We get something, and it's your job to sort of turn this into computer code, but with pen and paper you get this. You can implement that and use this LOG as a convolution mask for edge detection. And now, grand finale. Why should we do that? Actually, if we think of it, the difference between a Laplacian of Gaussian and the difference of Gaussian is not that big. So this is something you can verify at home. What I am saying here is that when we talked about the difference of Gaussians, like this one, that is the blue function. What this last slide said is that if we are given a Gaussian, say the red one, and compute its Laplacian, then it will look very similar to this blue one here. And that is to say that people, instead of using this, which is theoretically well founded, right? Because we say, okay, we are interested in edge detection, but we have to smooth first. Instead of smoothing first, we smooth or convolve with a smooth edge detector. Instead of doing this, people often just use this, because if you plot it, this difference of Gaussian looks very much like a Laplacian of Gaussians. It's theoretically not as well justified, but practically works beautiful, and it is better for the faint at heart, for those who are not comfortable with that. Nobody should not be comfortable with that, but you know, instead of doing that, people just do, once again, this. So what? Is basically practically hard to distinguish anyway. Theoretically, yes, practically, no. Now, what have we learned today? We have seen that this idea of median filtering, which we began to study last time, and which, if we were to compute it naively, is a rather expensive operation, can be done very efficiently as well. And then we ever so briefly talked about morphological operations, just because we already talked about ordered sets of local intensity values. We saw that these things provide interesting opportunities for, in particular, the area of shape processing. And then, ever so briefly, bilateral filtering, which is something that is extremely interesting, but unfortunately very, very slow. Really, seriously, even on modern computers, it's not instantaneous. Which was another nonlinear operation. These were operations that sort of depended on sorting. This one was a nonlinear operation that depended on an additional weighting factor. We then had some fun with Gaussian convolutions, where I say, well, let's smooth an image, subtract it, add the difference to the image, and it becomes sharper. Look at these slides I will upload, you see that. And next semester I'll do it with a much sharper mask. And then we discussed, again, Gaussians and Laplacians, and saw the difference of Gaussians, and we don't really see that, but the difference of Gaussians and Laplacians of Gaussians are very similar, and these are theoretically well founded concepts for image or signal processing. And to simplify our lives, we can also think of difference of Gaussians instead of Laplacians of Gaussians. So let's see, this one involved some Gaussian stuff, this one involved some Gaussian stuff, this one, so there's nothing we can do about this one, but these two things we can make fast. And next week we will study how that can be done. It will involve a bit of mathematics again, but we are by now used to that, and it is just not acceptable that we should be able to compute mean filtering in O of 1, median filtering in O of 1, and not Gaussian filtering. Next week we will learn how to do Gaussian filtering in O of 1. That is all I have got for today. Are there any questions? Yeah.
For the unsharp masking,
Yeah.
when alpha, we choose alpha equals to 1,
Mhm.
then we get unsharp masking, and if alpha larger than 1.
Yeah.
So how about alpha less than 1?
Then it will actually blur the image again. Right, so look, what happens is, let me see, we compute this residual here, right, between the original image and the smoothed version. This is the original image, this is blurred. You see that this is blurred. If you don't see that this is sharpened, but you see that this is blurred, okay? Now, if the size of this convolution kernel we use for blurring is not too large, and apparently it was not very large here because otherwise it would be very, very blurred. But if it is not a very large Gaussian, but rather a peaky one, then what is it that gets blurred? Like, for instance, the whiskers, right? So where the image is very sharp here, because the whiskers are rather edgy, just a few pixels, basically these are edges in the image. They are being blurred. If we subtract this from that, there are large parts of the image where it doesn't really matter if we blur, but where there are sharp contrasts in the image. And we saw that when we looked at the, was it here? No, wait. Bilateral filter. That this Gaussian blurring has the tendency to destroy edges. Right? And so therefore, in unsharp masking, it has destroyed the edges. In particular, these things have become blurred. We see that because this is where the difference between here and there is large. Can you see the whiskers here? Okay. Well, so if we add this back to that, it will emphasize edgy parts of the image. Right? The edgy parts of the image, if we add this to that, will become even brighter. Right? Because if we add, this is all 0 here, we add the 0 to here, nothing happens. But this is something white. If we add this white to something, it becomes even whiter. And you should see this here. Why don't you? It's the projector. Right? If alpha is less than 1, then this would be subtracted from this. Or it's like, weighted down. And so these sharp parts of the image would sort of dissolve. Yeah, that's it. So if you want to sharpen your image, you choose alpha at least 1 or larger. If it is larger than 1, it's called high boost filtering. It has dramatic effects. It really makes it look very uncanny, very, very sharp. Yeah. Any other questions? Great. So see you again next Monday then.